Yeah, thank you for the intro, Vigny. I'm very glad I could give this talk in person. Thank you all for showing up. My name's Tiger. I'm a third year at Yale University, and I'm excited to talk about what I've been working on for the past year, self-consistent. PhD, yeah, third year PhD student at Yale. Yeah, and I'm excited to talk about my work over this past year. Feel free to ask me any questions, interrupt me at any time. So yeah, this talk is, in a sense, kind of an advertisement for this code package I've written, so I'm going to start with the punchline right away. The REBOUND package now supports equilibrium tide theory and spin vector tracking. So if you're familiar with the package and familiar with the theory, feel free to just zone out after this point. Go to this link. The code is now all public. It's available for use. There's documentation and examples at this link here. Yeah, happy to answer any questions about installation or the science.
I wonder how many people are familiar with REBOUND.
Yeah.
Yep.
All right, so you guys can zone out now if you want. But yeah, so let's set the stage. For much of the history of the field of celestial dynamics, the regime that we've worked in has been that of point particles. And what that means is that the effect of the structure of each body is not considered. So in other words, the bodies are treated as, well, points. What that means in practice is that the dynamics of the system are fully described by this very familiar Newtonian point particle gravity. And if we call this the zeroth order approximation, this approximation is usually very good, right? Because for most astrophysical systems, will look something like this, where the distances are so vast that the structure of the bodies really is insignificant, right? You can't even see it. So in other words, again, just point particles. However, what about for those systems where distances aren't so vast? If we zoom in on a system like this, to first order and accounting for structure, the systems might look something more like this. Each body has some radius associated with it, as well as the distance from classical point particle dynamics. Each body is also spinning, where the magnitude and the direction of their rotation is parameterized by the spin axis, omega. So this is the quote-unquote first order. To second order, there's a few more effects to account for. Bodies are not perfect spheres. A body will be rotationally flattened and will also be deformed from tidal perturbers. So our bodies in this approximation are going to be oblate. The effect of tides also have to be considered. A tidal perturber will raise a tidal bulge on our planet. In the presence of dissipation, this tidal bulge will be slightly misaligned with the line of centers connecting the two bodies. This induces a torque on the orbit of the body, and this induces this change in angular momentum also changes the orbit, and it's another effect that we have to take into account. I want to emphasize the importance of spin-orbit coupling here. And what that means is the mutual dependence on the dynamics of the system versus the dynamics of a spin vector. So I'm going to show you a crude example of the importance of this spin-orbit coupling here. I'm going to show you a crude example of the importance of spin-orbit coupling. This is a plot from Milholland and Laughlin, 2019. We're going to get very intimately familiar with this plot over the course of this talk. But for now, I'm going to give a brief overview. So what's happening here is this is a system of three bodies. There's a central star and two identical planets. These two planets are initialized just wide of the 3:2 mean motion resonance, which means their orbital periods are in the simple integer ratio 3:2. A migration force is applied to both of these planets, slightly faster to the outer one, such that both of these planets are eventually caught into the 3:2 mean motion resonance, at which point they migrate inward in lockstep. So what's happening in this plot is this upper subplot shows the evolution of the semi-major axes of these two bodies, green the outer one, blue the inner one, and you can see that both planets migrate inward until they're caught into this 3:2 mean motion resonance. This black line shows the evolution of the period ratio, at which point this remains constant. But the more interesting plot is this bottom plot, which shows the evolution of the obliquities of both these planets. And obliquity here, yes, obliquity here refers to the angle between the orbit normal of the planet and the spin axis. In other words, the angle between the equatorial plane of the planet and the orbital plane of the planet, right? And there's obviously some very interesting obliquity evolution going on in this system. We'll take a deeper dive into the specifics of this obliquity evolution later on in the talk, but for now, it's enough to say that there's clearly interesting stuff going on, right? This plot was made using a fully consistent spin-orbit coupling code that accounted for this spin-orbit coupling effect. What happens when you don't do this? What happens when you evolve the dynamics of the system and then pass that into a simple spin vector equation of motion where the two don't talk to each other? Well, the evolution of the system is identical, but you miss all of that interesting obliquity evolution. And this is obviously a very crude example, but this does illustrate my point that
Why is it crude? Why are you using that word?
it's I guess
It's so beautiful and elegant to me. It's got everything.
I guess it is pretty. I guess what I did was very beautiful. Thank you, Rosemary.
No, it's crude.
Yeah,
Anyway,
yeah. Yeah, hopefully this gives some idea of the importance of spin-orbit coupling and these fascinating effects that you really just miss out on if you don't include. So to describe these forces, these effects, we're going to turn to equilibrium tide theory, which is a powerful framework that accounts not just for Newtonian point particle gravity, but for the structure of each body involved in the system. This equilibrium tide theory is developed first by Darwin in 1879 and expanded on by Alexander in 1973. And equilibrium tide theory, as the name suggests, assumes hydrostatic equilibrium. So for a fluid body in hydrostatic equilibrium, contours of constant density are going to coincide with contours of constant potential. So what that means is if you can precisely calculate the potential that a fluid body sits in, you're going to be able to deduce the body's shape. What that means in practice is for a body being perturbed tidally by a tidal perturber, you need to account for the potential of the body itself, the potential of the perturber, as well as the potential of the bulge that's raised by that perturber, which again is slightly misaligned with the line of centers. Now, of course, in practice, it's very difficult to do this. The shape and orientation of the tidally perturbed body is very sensitive to internal structure. So there is a need for another level of approximation. And I'm going to talk about one of them, which is the constant time lag model. As the name suggests, this approximation assumes that the tidal bulge is misaligned with the line of centers by a constant time, which we'll call tau here. A variety of authors have worked on expanding the constant time lag model, one of which Rosemary is sitting right there. And this model falls directly in the viscoelastic limit of Darwin's prescription. And using some simple energy and angular momentum arguments, you're able to derive the evolution of both the orbital elements of the system as well as the spin vector evolution of our two bodies. So we're going to take a closer look at the Eggleton, Kisilov, and Hutt formulation, which is the one that I've implemented in my code. So in this EKH framework, the Eggleton framework, which I'll call EKH, the distortion of each body is considered to lowest or quadruple order. This means that if you take an equipotential surface, you can define a volume radius r star, which is the radius this body would have if it was a perfect sphere. Then the actual radius r of the surface can be defined in terms of r star, where p2 is the second order Legendre polynomial, and alpha is this quantity relating to the internal structure, the rotation, and the companion, essentially the system state. But you're able to back out the potential from this distorted body. After this, you have to make two other assumptions to back out the equations of motion which we need. First of all, in a system without dissipation, energy is conserved. But in a system with dissipation, we assume that the energy dissipated, which is due purely to tidal dissipation, is a function of the rate of change of the body's shape. This is parameterized by this equation here. And using this, you're able to back out the magnitude of the tidal damping force. This Q term here is known as the quadruple tensor and is to first order. To first order gives the gives the shape of the body. So you're seeing the rate of change of shape here. Also notice the tau quantity, which is the aforementioned tidal dissipation parameter we're using. The second assumption we're going to make is the conservation of angular momentum. And angular momentum here, in this case, since we're dealing with structured bodies, includes both orbital angular momentum and spin angular momentum. This term is the orbital angular momentum of our body, and this term is the spin angular momentum. There's some terms here that I haven't defined yet, but we're going to get to them. And from this assumption, you're able to get the couple on the spin axis, and the differential equation describing the evolution of the spin axis is able to be backed out from this. So the system dynamics now are a lot more complex than just the simple point particle gravity that we're familiar with. You now have two additional forces. You have to account for the quadrupole distortion force, which accounts for the deviation from a perfect sphere of our body, and the tidal damping force. I'm now going to explicitly give the coupled equations of motions that we're using in this framework.
Sorry, can I ask a question?
Yes.
So isn't the system underdetermined? I mean, you said you have a rate of change of energy and rate of change of angular momentum, which you say is 0.
Yep.
Okay, so that's, you have a, on the other hand, multiple parameters describing both the spin and the orbit, right? Because you have the spin magnitude, you have the spin direction, so that's 3 parameters right there. You have the orbital semi-major axis and orbital eccentricity. So that, I'm counting more parameters in your 3 parameters here than equations that govern them. So how can you solve this the system? Well, so the spin is, okay, you know, let's say I have a single body, right? The spin is a vector, so that's 3 components.
Yeah.
And the orbit is at least 2 parameters, right? Semi-major axis and eccentricity. So that's already 5. Whereas angular momentum is a vector, so you have an equation for that. So that's 3 components there. Okay, all dl dt along all 3 components is 0, and you have a rate of energy change. So that's 4 equations and at least 5 unknowns. So how can you solve it?
Yeah, I understand your question. It's
shown us. You've
yeah.
shown us enough equations to do it.
Yeah, it's
Go back.
Okay, sorry, that is counted. I apologize.
The equation of motion is 6 basically. So there's d double F on the, and then there's this conservation of angular momentum from which you can write down omega dot. But the next page, go on with the next.
So that's 4 equations there.
Look, this one.
Ah.
The equation of motion of the relative motion. And so this is acceleration. They're actually accelerations, those F's, the way you measure them, not forces. I mean, force being in a basket. But anyway,
I must confess I can't recall the derivation off the top of my head, but the system is solvable with these assumptions here.
Okay, I'll ask afterwards.
Yeah, we can go. Yeah, I must confess I don't have the entire derivation. Yeah, and I'll give expressions for these 2 forces in the next slide here. Yeah. So yeah, this is the force. This is the quadrupole force, the tidal force here, and the differential equation describing the evolution of the spin vector. And I would like to draw attention to the fact that these are now coupled. So the dynamics of the system, the magnitudes of the quadrupole moment and tidal damping forces, depend on the spin vector, and also vice versa. Now let's talk about some of the parameters. In addition to the familiar mass, radius, distance, we have to worry about the tidal parameter, this tau quantity I described earlier. We have to worry about the K2 love number. This is a quantity that parameterizes the degree of central concentration in each body and is essentially a proxy for the internal composition. We have to deal with the spin vector, omega, and we also have to deal with the moment of inertia, I. As a very quick caveat, for many of you familiar with the exoplanet field, you may recognize that tau is not the tidal parameter of choice used in exoplanet science today, but it's rather this tidal quality factor Q, which is defined by this expression here as essentially a measure of the energy dissipated per tidal cycle. Now, you can relate Q to the angle between the line of centers and the tidal bulge, epsilon, using the so-called constant phase lag approximation, which is a different approximation developed by Goldreich in the 1960s. Now, the constant time lag approximation is believed to be more physically correct, but the constant phase lag model, due to its simplicity, has been widely adopted by the exoplanet community. And most people have good intuition for values of Q. Fewer people have good intuition for values of tau. In some cases, you're able to relate these two quantities using this expression here. You're able to relate the tidal quality factor to the constant time lag. And in fact, this is the relation used in Mardling and Lin 2002. And if you make this assumption, the two frameworks are equivalent. I do want to say that while we chose tau because we believe the constant time lag model to be more physically correct, in many cases, in almost all cases, this tau parameter is, both Q and tau are pretty poorly constrained, but Q is much better constrained than tau. So in practice, you may be forced to appeal to measurements of tau and use relations such as this one here to ultimately use the code.
Well, basically, they can measure Q, for example, with the Jupiter Io system. They can measure the Q values of both Jupiter and Io. But tau is well, it's not measurable in the same.
Exactly, yeah.
It's that your constant, it's Q. It's different for solid planets and gaseous objects, right?
Yeah.
So this
There
works for gaseous objects.
Yeah, there is a lot to go into debating the merits and the disadvantages of the constant time lag model versus the constant phase lag model. The constant time lag model, like Rosemary said, applies to fluid bodies better than solid bodies. But yes, there is a great deal of discourse between the two, and both models certainly have their merits and drawbacks. Sorry?
What is lowercase?
Oh, the mean motion, the orbital mean motion.
The orbital frequency.
Yeah.
See, that's a funny old term from ancient times. Mean motion. What the hell is that?
Yeah, the n is the tidal forcing frequency, which, for the traditional case of a moon orbiting a planet or such, can be approximated as the mean motion. But yeah, the framework that I've just gone over is extremely powerful, and many relevant and interesting results have been discovered using this framework. I could stand here all day and talk about them, but I'll just list two of these examples. So in 2007, Fabrique and Tremaine noticed a statistical excess of short-period binary stars with an exterior companion, and they showed that the phenomenon of quasi-cycles with tidal friction was able to greatly enhance the number of short-period binaries and explain this unusual distribution. Rosemary in 2007 developed a method to investigate systems at eccentricity fixed points and showed that by measuring the equilibrium eccentricity of the inner planets in these cases, you're able to get very powerful insights into the internal structures and tidal parameters of these bodies. So to recap, we need to account for four additional parameters describing each particle to go from point particles to our prescription. These are the spin vector, the Love number, the time lag tau, and the moment of inertia I.
Omega's three in it.
Yeah, the spin vector is really three parameters. It's omega x, omega y, omega z. Yeah. You also have two additional forces you have to consider, the quadrupole acceleration and the tidal damping. And you have one additional equation of motion that you have to integrate, the spin axis equation of motion, along with your equations of motion for the dynamics of the system. And again, the forces and the spin axis equation of motion are coupled. So yeah, now with that background out of the way, I can dive into the actual code a little bit. So what is REBOUND? REBOUND is a widely used n-body integrator package. An n-body integrator simulates the effects of particles, simulates the motion of particles under the influence of gravity. Rebound includes a variety of integrators, including symplectic integrators, non-symplectic higher order ones, as well as hybrid integrators that are a combination of both. So it can be thought of as an integrator package, not just a simple n-body integrator. There's C source code as well as a convenient Python wrapper. And one of the great advantages of Rebound is it's very widespread. It's easy and intuitive, and it's very, very flexible. It's simultaneously powerful enough for research-grade publications and also for undergrads to pick up for their first year in astronomy. So I think very highly of this package. I think I'm allowed to brag about it a little bit because I didn't really write the source code. I only wrote the additions. This is all Han O'Brien. Yeah, Rebound X is a package of additional physics that may be added in modular fashion to a rebound simulation. These effects include things like mass loss or gain, disk migration, radiation forces, general relativity, stochastic forces, and also now equilibrium tide theory, of course. So the paper that we wrote with Rosemary describing our implementation of these forces in the rebound framework is now in review. Thank you to all the co-authors for this. The paper is not public yet, but I'm happy to share the manuscript with any of you if you want to, and talk over it if anyone has any questions about it. But yeah, while other such codes do exist right now, such as Mercury T, we believe that due to the integration of Rebound, our code comes with a number of advantages, which includes ease of use, compatibility with all the Rebound integrators and other Rebound X effects, and leverages Rebound's already widespread use. For anyone who already uses Rebound, this will be a pretty small barrier to entry. So some quick notes. The ODE integrator uses a Berle-Stower integrator by default. It's compatible with any other integrator for the system dynamics, but the spin vector integration uses BS. We include some helper functions to convert Q from tau. So everything in our code on the back end uses tau as the parameter of choice. If you only know Q for your bodies, we do provide some helper functions to, under the hood, use Q instead of tau in the equations of motion. We support a mixture of point particles and bodies endowed with structure. This is very important because while these effects are always present, sometimes they're insignificant if their distances are great. So this helps the simulations not rapidly get out of hand computation-wise. And currently, we assume a constant number of particles. So sadly, at the moment, the code does not support particles disappearing or getting ejected, but hopefully working on that in the near future. I've just attached some quick snippets of the code used for both the C and Python versions. Really is pretty simple to set up. So yeah, again, I'm going to shamelessly advertise again. Documentation is here. The GitHub is here. Here are some good here are some example notebooks and example files you can use down here, which are all in the GitHub. And yes, again, feel free to ask me if you have any questions about the use of it. But OK, now we'll get into some science, and I'll talk about how our code performs against analytic predictions and against previous results. So a pretty simple and obvious test of our code is a comparison with secular orbit average expressions. We compare against the analytic expressions of LeConte et al. 2010, which were derived from an equivalent framework to the EKH framework, the HUT framework. These expressions here are these analytic expressions. And essentially, what they predict are tidal circularization. So a planet's orbit, if it starts out eccentric, will quickly reach very low eccentricity. It predicts obliquity damped to 0. So in other words, it predicts that the orbit normal of the planet and the spin axis of the planet will quickly synchronize and point in the same direction. And it also predicts that the spin of the planet will rapidly evolve to a pseudo-synchronous state, which I'll go into in a little bit more detail later.
So these are just for two bodies, just to be clear.
Yes, this is just for two bodies. These equations describe two bodies. So we perform a basic test integration illustrating the spin-down and tidal circularization of a fiducial hot Jupiter orbiting a basic sun-type star. We initialize the hot Jupiter with a non-trivial 30-degree obliquity. So these black curves represent the predictions from the analytic expressions on the previous page. And these red dots represent the numeric predictions, our numeric results. And you can see there's very good agreement between the analytic and numeric results. As predicted, the obliquity does rapidly damp down to 0, and the spin rate evolves to this pseudosynchronous state, which I haven't defined yet, but I will define now. Pseudosynchronization is one of the primary predictions of the equilibrium tide theory, which states that the spin rate of a planet will rapidly evolve to this pseudosynchronous equilibrium value, which is given as a function of eccentricity up here. So what we ended up doing to test this was we ran this simulation here 80 more times with the same initial conditions, except varying the initial eccentricity of our system from 0 to 0.8. Evolved each simulation for 1 million years and plotted the final spin rates. So again, the black curve here is the analytic prediction of what the pseudo-synchronization curve should be, and the red points are the results from our simulations. And again, there's fantastic agreement between the analytically predicted pseudo-synchronous curve and our numeric results. Our next benchmark is against independent results. So again, this is the plot from Milholland and Laughlin 2019. And the punchline of this is really in the blue planet here, where this result showed that convergent migrations in many of the Kepler-like systems can be expected to drive and generate high obliquities. And this source of obliquity tides has been brought up as a potential reason for the slight statistical excess of planets just wide of mean motion resonance.
Can I just throw, so just to make so you've got two planets now and one star, 3 bodies, not just 2 bodies. So the equilibrium states are different to what they would be just with 2 bodies, just to sort of fill in the story. Yeah.
Exactly.
For the audience. Yeah.
And this the bottom subplot here represents some of the important precessional frequencies we're going to deal with. And I'll go into a little bit more detail about that now, because to understand these results, we need to give a very brief crash course on the phenomenon of spin-orbit resonance. This is a process that involves 2 key frequencies. The first of which is the so-called axial precession rate. In the presence of torques from the host star or a satellite system, the spin axis of a planet is going to precess or rotate about the orbit normal. The speed of this precession is defined by this axial precession rate constant alpha. The second relevant frequency that we need to consider is the nodal recession rate g. So in the presence of torques from other bodies in the system, other planets, for example, the orbit normal of your planet is going to recess about the invariant plane of the system, where the invariant plane is just the total angular momentum of the system. And the speed at which the planet's node recesses about the invariant plane is given by this g quantity here. And g is just the rate of change of the longitude of ascending node of your orbit. But that's the other relevant frequency we have to deal with. What you're looking at here is a little bit complicated, but it is the evolution of spin axis trajectories for various values of this ratio alpha over g. So what's plotted here are level curves of the spin axis Hamiltonian. These gray lines here. What you can think of them is you can think of it as looking at a planet from a polar view, top down. And these gray curves are curves that the spin axis is going to evolve on. So if you initialize your spin axis on one of these gray curves, what it's telling you is that the spin axis is going to evolve along this curve, right? So it's just going to spin around like this. Now, the landscape of this phase space, the landscape of this phase space trajectory is highly dependent on this ratio alpha over g. And you get interesting behavior when this ratio approaches unity. So if you see far away from unity, where the ratio g over alpha is roughly equal to 3, there's not much interesting behavior. All your spin vectors just kind of precess around the orbit normal, kind of just in a pretty boring circle. But when you get closer to this critical alpha over g equals 1, you start to see some interesting behavior. And it turns out this is kind of the process of resonance capture, because if the ratio alpha over g evolves slowly enough, your spin vector, as these gray curves change, your spin vector is going to stay on the same curve. And as your gray curves move to higher and higher obliquities, your spin vector is going to stay on that curve, and it itself will be pushed to higher obliquities. So this is a pretty well-studied process, and it's been plausibly shown to be responsible for the obliquities of Jupiter, Saturn, and potentially Uranus as well. And this is the process that excited our planet in the earlier Milholland and Laughlin simulation to high value because of this crossing of alpha and g. So again, I'm going to throw up the results from Milholland and Laughlin 2019 on the left-hand side for you guys, and our results of the simulation with the same initial conditions on the right side. Now there's a bit to take in here, but first of all, notice that the qualitative end state of the simulation is the same. So kind of, again, the punchline of the Milholland and Laughlin simulations was that convergent migration of these two bodies was able to excite and maintain a high obliquity for the inner planet indefinitely. And you see the same thing with our simulations. The inner planet is excited and indefinitely maintained at around 50 degrees, essentially indefinitely. So that's qualitatively everything's the same, but obviously nothing's quite the same. There are a few things that aren't quite the same, right? I'd like to draw your attention to the green curves here, which is the obliquity of the outer planet. And in particular, this regime between the two gray lines is different, right? In the original simulation, you see two sudden kicks in resonance, whereas in our simulation, you see a more gradual resonance capture and then being damped back down to 0 degrees. So we have, by the way, how am I doing on time? I'm good? Yeah. Oh, the clock. Excellent. Yeah. So we have investigated the evolution of the spin vector in this interesting regime. So this is again on the left-hand side are the results from Milholland and Laughlin 2019. On the right-hand side are our results. These top subplots represent the inner planet. The behavior is the same in both cases. This bottom subplot represents the difference in evolution of the outer planet, which, again, just to remind you, you see this difference in obliquity evolution here. And what's going on with the Milholland and Laughlin simulation is that the spin axis is just kicked from this large circulating trajectory to a smaller circulating trajectory. What's happening in our simulations is it starts on the same large circulating trajectory, but then it's captured into these resonant banana-like librating trajectories, where librating means it doesn't do a full 360-degree revolution around the center, but rather it's caught in this kind of resonant zone, right? So we're not 100% sure what is causing we're not 100% clear what the true genesis of the difference is between our. We haven't gotten around there yet. Yeah, we can discuss it later. But for now, I can throw up a theory that we have, which we are going to investigate in a little bit. And Rosemary would love to talk about this further. But essentially, the process of resonant capture, we believe, is highly dependent on the highly sensitive to initial conditions and the precise position of the spin vector at the moment of resonant capture. What this means is if you have at the moment of resonance capture, if you have two spin vector initializations that are very close to one another, they can be kicked to different sides of the resonant domain. And as the system evolves, a slight difference in initial conditions can lead to very different system evolutions. But of course, as the system evolves back into the original state as a result of the system evolution, despite this overall evolution change, you're going to end up back in the same state because you're going to return to this. I don't know how clear that was, but look out for a new paper soon on that in the somewhat near future, where we explore the precise dependence of resonance capture on initial conditions. Yeah, so I'm just going to briefly touch on one more thing we put in the paper, which is a small exploration of the von Zeipel-Leadoff-Kozai effect, which is a process of angular momentum exchange in three-body systems between, in a hierarchical three-body system where you have a star, a planet orbiting the star, and a binary star far away from it all. And just to briefly touch on what we showed here, we showed a relatively boring result that the end result of planetary obliquity at the end of these Kozai cycles show that the planetary obliquity should be very close to 0. But we're also in the process of investigating this. So yeah, here are some future directions I'm interested in taking this code. If anyone is interested in any of these projects, please, I'm very happy to talk about any of them. One of them is the observed sub-pseudo-synchronous rotation of HD 80606b, which is one of the most eccentric exoplanets we know of today. The interesting thing about this planet, HD 80606, is, recall earlier I talked about the predicted equilibrium pseudo-synchronous state that planets are supposed to be rotating in. Well, in 2009, there were Spitzer Space Telescope observations of this planet, which showed that this planet was actually rotating much slower than the pseudo-synchronous rate. So an exploration of that is probably worth doing. I'm also very interested in the obliquity evolution of TRAPPIST-1 and other resonant chains as a consequence of disk-driven migration. TRAPPIST-1 is a system where you have 7 planets, each in what's called a resonant chain. So each of the 7 planets are in mean motion resonance, where their periods are in small integer ratios of one another. It's believed that these systems were formed as a consequence of disk-driven migration. And if you recall the Milholland and Laughlin 2019 paper, this process may excite orbital obliquities, may excite planetary obliquities. So a closer look at the obliquity evolution as a consequence of disk-driven migration is something I'm very interested in. And also processes involving, also a closer look at some hypotheses we have about Uranus's obliquity, and resonances therein is also on the list. So yeah, thank you for listening to my talk. I'm going to put up the relevant links to the code again, and here are some of the various ways you can contact me. Thank you for your attention, and I will take questions.
Yeah, thank you, Tiger. We have plenty of time for questions.
Yeah.
Let's start with Rio. Thank you.
Yeah, thanks for the great talk. So you had the input parameters, and one of them was this constant phase and time lag. I can see how you can set that for a binary, but when you have multiple bodies, do you need like that phase lag for every single combination?
See, that's an excellent question, and that was the source of that was the source of a lot. Rosemary knows this was the source of a lot of confusion for me. The punchline is, so in each of these, so there's a constant phase lag approximation and a constant time lag approximation, right? In the constant time lag approximation, yes, this time lag tau, it's intrinsic to each body. So tides. So if you have multiple bodies raising a tide on this, if you have body A and body B raising 2 different tides on body C, yes, body C in both cases, the bulge raised by each of those bodies lags by time tau. And the same thing for the constant phase lag approximation. They'll lag by a common phase. Now the exact validity of that approximation is something worth talking about in detail. But yes, that's in each of these approximations, both of those is an intrinsic quantity for each planet.
So in the results you showed, do you like just set the same value for everything, or?
In which result?
Well, like your, what is it, the resonance capture stuff, or like you have more than 2 bodies, right?
Yeah. So in this in this, what we did was we set a constant q using the relation q equals 1 over 2n tau. We use the same q for both bodies. Now, in this prescription, this does imply, right, that the taus are different for each body. So while the bodies are identical, this does imply that you have different internal structure. We just did this to exactly replicate the Milholland and Laughlin 2019 results, where they did use the same q for both the results, since they used the Marley and Lin 2002 prescription, which uses q instead of tau. In practice, it doesn't matter too much. The effects of planetary tides are the specific on the specific parameters doesn't really change the qualitative evolution so far. And this is a source of a lot of debate in the planetary tidal evolution community right now. And the truth is, these parameters are just, at the moment, so poorly constrained that while it is true that maybe some of the understanding is incorrect, it doesn't seem worth it to get too deep into the weeds on the precise values of q or tau at the moment.
Any more questions?
Thank you, and thanks for the really nice talk. So I was going to ask about the synchronization. Well, the expression you have for the synchronization frequency that you have right there for a slightly eccentric orbit. But actually, I realized maybe it's a more general question. What are the conditions under which these equilibrium tides you think are applicable? So is there, for example, a range of eccentricities where if the eccentricity is too high, you have to switch to dynamical tides? And is there something that you have to assume about the composition or structure of the object experiencing tides for equilibrium tides to be relevant?
That is another fantastic question, and I don't think there's a right answer to your question. It's not a equilibrium tides are dominant here and dynamical tides. There is a spectrum. What I will say is that in principle, the equilibrium tide theory this framework of the equilibrium tide theory at least is in principle valid to any degree of eccentricity. So the constant phase lag model, the opposing approximation, is only valid to, I think, second order in eccentricity. This is in principle valid to any degree in eccentricity. But you're right. Equilibrium tides, while very elegant and powerful, is probably not the most rigorous tidal rheology. You have to appeal to dynamical tides at some point.
The thing is, you don't have an actual equilibrium tide unless you have a circular orbit, right? That's a true equilibrium tide, where the tidal bulge follow when those things relax completely. The bulges follow each other around the orbit, and the fluid doesn't move in the rotating frame. That's a true equilibrium configuration. Any departure from that means there is a dynamical tide. So really the question is, when does one matter more than the other, etc., etc. So for a dynamical tide, the frequency of oscillation are intrinsic frequencies, the response of the star, and the equilibrium tide, the idea behind it, the forcing frequency is the orbital frequency. So really I would say generally high eccentricities you really need to be doing a dynamical tide, and even though Hutt and others have these high, this is an exact expansion in this secular approximation really. It implies you can have high eccentricities, and we do that, but it's not very physical.
One interesting example that's pertinent to that question was the example of HG 80606, which I talked to Vigny about just a little earlier at lunch, but also.
Eccentricity is 0.93, by the way. I mean, it's really worth saying. It's crazy.
I believe that's either the most eccentric or the second most eccentric exoplanet we know
And
of.
a transit, they caught it in transit thanks to his supervisor.
Yeah, a very brief tangent, but my supervisor Greg is very cynical about a lot of scientific things, but he he loves this system because he says that this system has always delivered for him. Whenever he looks at it, something interesting comes out. But yeah, as I said, in 2009, the Spitzer Space Telescope took a thermal phase curve, which is kind of depicted here, which they're able to infer the rotation rate of the planet out of. The pseudo-synchronous expected equilibrium rate from the expression I gave earlier is you'd expect HD 80606b to be rotating with a period of about 37 hours. They measured a 90-hour rotation period. So that's a there are a number of potential explanations for that. But yeah, one possible explanation is what if it's not in the expected pseudo-synchronous rotation period, right? And you would have to appeal to something other than equilibrium tides to explain that.
Well, it might be in an interesting spin-orbit resonance.
That is another fantastic, yeah. They're again the system that keeps on delivering, right? Yeah.
But I mean, do you also have to assume something about the structure of the planet, for example, for equilibrium tides to be relevant, right? I mean, for stars, we talk about convective versus radiative stars, right? And equilibrium tides are presumably relevant for convective stars, right? But for planets, is it safe to apply it for all planetary types?
So this was developed for fluid bodies in particular, so like gas giants. The formalism that better describes rocky planets is the constant phase lag model, which basically what the constant time lag model is saying is that the phase angle between the, let me pull up the what the constant time lag model is saying that this angle here depends on the frequency of the tidal perturber, right? It depends on, for example, the mean motion. The constant phase lag model says that no, it doesn't. No matter what the frequency of your tidal perturber, this angle is going to remain the same. And this was actually based on laboratory experiments, which showed that for rocky or solid objects, this quality factor Q, or the lag angle, was not dependent on the forcing frequency. So yes, it appears that there's two competing approximations, which, yeah, yeah. Did that answer your question?
Thank you.
So the other point, of course, is that you have an equilibrium state, but just having an equilibrium state doesn't mean you are there instantaneously. So it may also take a while to get equilibrium, especially if you have these things with these very long orbits, and you have this forcing only when it gets very close, and you have to wait again for a really long time. So it may take a while before it actually gets in equilibrium.
Yeah. Are you
sorry?
Well, talk about it. I don't agree.
What is the time scale?
Are you talking about the time scale for the tidal bulge to assume tidal equilibrium?
This co-rotation. It will take. I mean, it won't happen at the first interaction. It will take a few orbits to go.
A few orbits?
Yes, many,
Yeah.
exactly. So the question is, what's the time scale compared to the age of the system?
I wasn't aware that it was on the time scale of many orbits. I thought it was fast.
To get
Yeah.
into these tidal equilibrium states.
Oh, I thought you meant the bulge reacting to the potential. No. You're exactly right about that. Yeah, reaching the final tidal equilibrium state.
And it's not it's a pseudo equilibrium state. This is for this, these eccentric orbits. That's not an equilibrium state. I mean, it's the orbit.
So what is the time scale?
There's all sorts of.
You're talking about like the pseudo-synchronous.
Yes, the time scale to reach
That's the
equilibrium.
fast one. The spin.
I don't know the exact time scale off the top of my head, but yeah, you're a few orbits on.
Many.
Okay, maybe last question by Daniel.
I was just curious about Uranus. So, in particular, you had something on your last slide about Uranus.
Yeah. I
Start with some non-zero obliquity. I mean, is Uranus in some kind of what do you call it, like steady state or something, equilibrium state?
yeah.
So
So
we remind people it's tilted by 97 degrees to its orbit around.
So yeah, I didn't get too deep into this because I realized right when I started talking about how deep, and I'm happy to talk about this more later. But to give a brief rundown, the Uranus is tilted 98 degrees, and the primary the most well accepted hypothesis is the giant impact theory, right? That like a giant impactor tilted Uranus over. The problem with that theory is the most widely accepted theory for a good reason, right? It reproduces most of the current characteristics of Uranus, but the problem with it is Uranus' satellite system. If you have Morbidelli in 2012 showed that if you had one impactor tilting Uranus over from 0 to 98 degrees, the satellite system would orbit the opposite way that it's currently observed to orbit, right? So what Morbidelli proposed was a two-step process where two impactors, one brings it halfway, and the second impactor brings it to 98 degrees. Well, which, while still possible, is obviously a lot less likely, right? So over the past couple, maybe decade or so, there's been a lot of effort to find alternatives for the evolution of Uranus. And spin-orbit resonance has been one of those, the spin-orbit resonance process I described in Milholland and Laughlin. The issue with spin-orbit resonance is that it's just very difficult to get to 98 degrees in the first place with spin-orbit resonance. Most of the literature for spin-orbit resonance for Uranus specifically have only been able to bring it to around 50 or 60 degrees. So yeah, what we're proposing here is somewhat of a hybrid method that involves one impactor and spin-orbit resonance. And that would take a while to get into, but I'm happy to talk about that after the talk if you're interested.